Example, a pharmacy has a uniform annual demand of 200 bottles of a certain antibiotic. It costs $10 to store one bottle for 1 year and $40 to place an order. How many times during the year should the pharmacy order the antibiotic in order to minimize the total storage and reorder costs? When solving application problems, we should identify first what questions we're asked to answer. For this one, we need to know how many times to place an order. So, we'll let X be the number of times the pharmacy places an order, and for the 200 bottles of uniform demand, how many demands? We'll let Y be the number of demands. Now, what is our goal or objective? The goal is to optimize the cost. That is, have the least or minimum cost possible given the constraints. The cost has two parts: the cost of ordering and the cost of storage. The cost of ordering is $40 per order, and we're looking for X, the number of times to order. So for that part, C equals 40 times X. Now to the cost of storage. We are looking at a graph in the first quadrant with 0, 1/2, and 1 marked on the y-axis with a dashed horizontal line through the 1/2. The pharmacy has uniform demand, so the quantity depletes at a constant rate. That means the number of bottles in storage between reorders will decrease from Y to 0, and the average number in storage each time period is 1/2. So, with the cost of storing one bottle at $10 and the number of demands at Y/2, we get of the storage as 10 times Y/2. Let's simplify to get C equals 4X plus 5Y. X is the number of orders, Y is the number of demands. The goal is to optimize the cost, which is represented by C equals 40X plus 5Y. This is a function of two variables, X and Y, and we need this function to be expressed in terms of only one variable. To do so, let's use a constraint given in the problem. The constraint we have is that the annual demand is 200 bottles, and the annual demand is met as the product of the number of orders and the number of demands. So we have X number of orders and Y number of demands, and that equals 200. We'll solve for Y by dividing by X on both sides, and we get Y equals 200 divided by X. Now we can express the cost as a function of only one variable. I choose X by substituting Y with 200 divided by X. We get C of X equals 40X plus 5 times the quantity 200 divided by X. Let's multiply together the 5 and 200, and we'll get 40X plus 1,000 over X. We need to now specify the domain. Algebraically, X cannot equal 0 because that allows for a 0 in the denominator. And for this real-world problem, we need a real-world constraint. The number of times the pharmacy places an order cannot be negative, so we write that X is greater than 0. We need to optimize the cost function C of X equals 40X plus 1,000 over X for X greater than 0. With cost, optimize means minimize. We can use the first derivative test or the second derivative test for this purpose. Regardless of the test we choose, we need to solve for critical values. Critical values are the X values in the domain of the function where the first derivative equals 0 or the first derivative is undefined. Before taking the derivative, let's rewrite the cost function as C of X equals 40X plus 1,000 times X to the minus 1. Expressing the 1 over X as X to the minus 1 lets us use the power rule. Now we'll find the derivative. C prime of x is 40 minus 1,000 times x to the minus 2. The derivative of 40x is just 40. We bring down the minus 1 multiplied to the 1,000. That makes it minus 1,000. And then x to the power of negative 2. We express that as 40 minus 1,000 over x squared. Now, even though the derivative is undefined at x equals 0, it is not a critical value because 0 is not in the domain of the function. So, we now solve for the first derivative set equal to 0. We're going to set that first derivative equal to 0, but first we're going to get a common denominator and combine terms. So we'll have that 0 is equal to 40x squared minus 1,000 divided by x squared. The numerator has a common factor of 40, so let's take that out, and we'll get that equal to 40 times, and in the numerator, x squared minus 25 in parentheses, the denominator stays the same. It is still x squared. Now, we can solve this equation as 0 equals 40 times x squared minus 25. What happened to the denominator? Well, when a fraction equals 0, the numerator has to equal 0. We're not concerned with the denominator here because the domain restriction guarantees that the denominator cannot equal 0. So we'll continue working with the numerator. We'll factor the difference of squares, x squared minus 25. And now we can write that as 40 times x plus 5 times x minus 5. Let's set those factors equal to 0, and we get that the critical values are equal to x equals negative 5 and positive 5. However, the domain of C is strictly greater than 0, so negative 5 is not a critical value. We'll use the second derivative test to determine extrema. Remember, we solved for the first derivative, which was c prime of x is equal to 40 minus 1,000 times x to the power of negative 2. And we had a critical value at x equals 5. To use the second derivative test, we need the second derivative. So let's solve for that. C double prime of x is equal to, the 40 goes away. Bring down the negative 2 and multiply it to the negative 1,000, which will give you positive 2,000 times x to the power of negative 2 minus 1 is negative 3. Let's go ahead and express that as a rational expression. So we'll have 2,000 divided by x cubed. Now we need to evaluate that second derivative at the critical value of 5. That is, we need c double prime of 5 and compute that with 2,000 over where the x was, we put in 5 cubed. We're not concerned with the actual number. We're only concerned with whether or not it's positive or negative. Since you're dividing a positive number by a positive number, we know that that's going to be positive or greater than 0. And when the second derivative is greater than 0, then we have concave up. And when you have concave up, the most extreme point is the minimum. So we have a minimum at x equals 5. We have found the critical value, and we have demonstrated that that critical value leads us to the minimum cost. So the pharmacy should reorder 5 times to minimize storage and reorder costs. The minimum cost is $400. How did we get that? You evaluate the cost function at the critical value of x equals 5, which gives the minimum. So C of 5 is equal to 40 times 5 plus 1,000 over 5, which is 200 plus 200, where we got the 400.